places on Earth where the rules seem to break, landscapes where rivers glow in unnatural colors, where the ground breathes heat from deep beneath the crust, where entire valleys look as though they belong to another planet, silent, hostile, and almost impossible to comprehend. At first glance, these environments appear unreal, too extreme, too strange, too precise in their formations to be natural. And yet they exist, not in distant galaxies, but here, on our own planet. In Ethiopia, acidic pools bubble in colors that resemble chemical reactions more than nature. In Iceland, ice caves glow with an electric blue light that seems engineered rather than formed. In Namibia, trees that died nearly 1,000 years ago still stand, perfectly preserved against a lifeless white desert floor. These are not anomalies. They are evidence, and evidence that Earth is far more dynamic, volatile, and unpredictable than we assume. But what creates these places? Why do some regions of Earth begin to resemble alien worlds? And what do they reveal about the deeper forces shaping not just our planet, but potentially others? This is not just a journey across landscapes, it is an investigation into the limits of nature itself, where geology, chemistry, and time converge to create environments that challenge our understanding of reality. A planet that defies expectations. From orbit, Earth appears calm. A sphere of deep blue oceans, soft white cloud systems, and stable land masses that suggest balance. It is often described as a habitable planet, predictable, life-supporting, and understood. But this image is deceptive, and beneath that thin atmospheric veil lies a world defined not by stability, but by constant transformation. For most of human history, our understanding of Earth was limited to what could be seen, crossed, and survived. Early civilizations mapped rivers, mountains, and coastlines, building a sense of familiarity with their surroundings. This created an assumption that the planet was largely uniform, governed by consistent rules. That assumption began to collapse with exploration. As expeditions pushed further into remote regions, they encountered environments that did not behave as expected. Landscapes where water was toxic, where heat emerged directly from the ground, where entire ecosystems operated without sunlight or oxygen in familiar forms. These were not gradual variations of known terrain. They were extremes. In the 19th and early 20th centuries, geological surveys and polar expeditions documented places that seemed incompatible with life as it was understood. The interior of Antarctica revealed a frozen desert with almost no precipitation. Volcanic regions exposed liquid rock and gases, reshaping land in real time. Isolated islands developed ecosystems so unique that species evolved independently, following entirely different biological paths. What emerged from these discoveries was a new realization. Earth is not a single environment. It is a collection of systems, dynamic, often unstable, and sometimes hostile. These systems interact through tectonic movement, atmospheric circulation, and chemical processes that operate on timescales far beyond human perception. The result is a planet capable of producing environments that feel alien, yes, not because they belong elsewhere, but because they reveal aspects of Earth we rarely see. Understanding these places requires more than observation. It demands investigation into the forces beneath the surface, the chemistry of extreme conditions, and the history written into rock, ice, and water. Because what appears impossible is not an exception. It is evidence of how this planet truly works. Fire beneath the surface. Beneath the surface of the Earth, the planet is not solid. It moves. At depths unreachable to direct observation, immense harara and pressure reshape rock into molten matter, magma. This internal heat is not uniform. It concentrates along fractures in the Earth's crust, where tectonic plates pull apart, collide, or slide past one another. These boundaries become gateways, allowing the planet's internal energy to reach the surface. Places like the Danakil Depression in Ethiopia, this process is exposed with unusual clarity. Here, 3 tectonic plates are slowly diverging, thinning the crust to the point where magma rises closer to the surface than almost anywhere else on Earth. The result is a landscape defined not by stability, but by chemical activity. Pools of liquid sulfur form in shades of neon yellow and green. Gases rich in hydrogen sulfide escape through vents, reacting with oxygen in the air to create sulfuric compounds. The ground itself becomes unstable, layered with salt deposits and mineral crusts that shift underfoot. Temperatures routinely exceed 45 degrees Celsius, and the combination of heat and toxic gases creates an environment where human survival is measured in minutes, not hours. But thousands of kilometers away, in Nevada, a different kind of geothermal anomaly rises from the desert. Fly Geyser was not formed by tectonic exposure, but by accident. In 1964, a drilling operation punctured a geothermal reservoir. Superheated water began to escape, carrying dissolved minerals to the surface. Over decades, these minerals accumulated, building terraces that continue to grow. Thermophilic microorganisms colonize the structure, feeding on heat and minerals. Their presence transformed the geyser's appearance, coating it in reds, greens, and oranges. What appears artificial at first glance is, in reality, a collaboration between human error and natural adaptation. In Indonesia, the Ijen crater presents yet another variation of geothermal intensity. At night, a rare phenomenon becomes visible: blue flames moving across the volcanic surface. These are not flows of lava, but ignited sulfuric gases escaping through cracks in the rock. When these gases combust, they produce an electric blue dough, often mistaken for molten material. At the center of the crater lies one of the most acidic lakes on Earth, with a pH approaching 0. Its ilmia are saturated with dissolved metals and sulfuric compounds, creating a chemical environment closer to industrial acid than natural water. These locations are not isolated anomalies. They are expressions of the same underlying process: a planet releasing its internal energy. Through heat, pressure, and chemistry, Earth reshapes its surface continuously, creating environments that appear alien, but are, in fact, fundamental to its nature. This is not destruction, thus it is construction, operating at a scale and intensity that challenges human perception. Ice that behaves like light. At first glance, ice appears static, a solid state of water, defined by stillness and cold. But in reality, ice is dynamic, constantly shifting, compressing, and responding to forces that operate both above and below the surface. Nowhere is this more evident than in the glaciers and ice systems that dominate the polar and subpolar regions of Earth. In Iceland, beneath the vast mass of Vatnajökull, ice behaves in a way that challenges perception. Glacial caves form not through emptiness, but through motion. Meltwater carves tunnels through dense ice, reshaping internal structures with seasonal precision. These caves are temporary, often collapsing and reforming within a single year. What gives them their striking blue color is not pigment, but physics. As snow accumulates and compresses over time, air bubbles are forced out, creating dense, pure ice. When light enters this structure, longer wavelengths, reds and yellows, are absorbed, while shorter blue wavelengths scatter and reflect back to the eye. The result is an intense, almost artificial blue glow, as if the ice itself is emitting light. But this visual effect reveals something deeper: time. Each layer of compressed ice represents years, sometimes centuries, of snowfall. The cave walls are not just structures, they are records, preserving atmospheric conditions from the past in frozen form. Further south, Antarctica expands this phenomenon to a continental scale. Here, ice does not simply cover land, it defines it. The Antarctic ice sheet holds nearly 70% of the world's fresh water, locked in layers that can reach several kilometers in thickness. Beneath this immense weight, the Zamin itself is depressed, forming subglacial basins and lakes hidden from the surface. One such environment is Lake Vostok, buried beneath more than 4 kilometers of ice. Isolated for millions of years, it represents one of the most extreme ecosystems ever discovered. Scientists studying these lakes are not only investigating Earth's limits, but also testing hypotheses about life in similar environments beyond our planet, such as the subsurface oceans of icy moons like Europa. Despite its still appearance, Antarctic ice is in constant motion. Glaciers flow outward under their own weight, slowly transporting ice from the interior toward the ocean. But when these massive structures fracture, they release icebergs, some the size of cities, into surrounding waters. This is not a frozen world. It is a system in motion, governed by pressure, temperature, and time. A system where light is filtered, history is preserved, and entire landscapes move at speeds too slow for immediate perception, but powerful enough to reshape continents. In these environments, ice is no longer just matter. It becomes structure, memory, and light. Deserts that break the definition of desert. A desert is often defined by absence, an absence of water, an absence of life, an absence of change. But this definition is incomplete. Some of the most visually complex and scientifically unusual environments on Earth exist within deserts, places where the lack of moisture does not simplify the landscape, but instead preserves it, transforms it, and in some cases contradicts the very idea of what a desert should be. In Namibia, within the Namib-Naukluft region, lies Dead Vlei, a clay pan surrounded by some of the tallest sand dunes on Earth. The scene appears almost constructed: a white, cracked surface, skeletal black trees, and towering dunes glowing deep red under direct sunlight. The trees, primarily camel thorn acacias, died approximately 900 years ago, yet they remain standing, not fossilized, but preserved. The explanation lies in extreme aridity. Without sufficient moisture, the microorganisms responsible for decomposition cannot function. Time in this environment slows to a near halt. But Deadvlay is not defined only by preservation. It is also the result of interruption. Thousands of years ago, a river once flowed into this basin, supporting vegetation. Over time, shifting dunes blocked its path, cutting off the water supply entirely. What remains is a snapshot, an ecosystem frozen at the moment of its collapse. Further west in Brazil, the Lençóis Maranhenses challenge the desert definition from another direction. At first glance, it resembles a conventional dune field, vast, rolling white rimmel shaped by wind. But during the rainy season, something unexpected occurs. Rainwater accumulates between the dunes, forming thousands of temporary lagoons. These pools are not superficial. They can reach depths of several meters and stretch across kilometers. The underlying geology, a layer of impermeable clay, prevents water from draining, allowing the lagoons to persist for months. Even more unusual is the presence of life. Certain species of fish survive by leaving dormant eggs in the sand during dry periods. When the rains return, the eggs hatch, repopulating the Ilmia in a cycle that appears almost improbable. In Chile's Atacama Desert, often considered the driest non-polar place on Earth, entire regions can go years without measurable rainfall. Yet even here, life adapts. Microbial communities persist in salt crusts, extracting moisture directly from the atmosphere. These deserts are not empty. They are precise, shaped by wind patterns, geological barriers, and rare but significant interactions with water. They preserve what other environments erase. They create contrasts so sharp between life and death, wet and dry, movement and stillness, that they begin to feel artificial. But nothing here is accidental. These landscapes are the result of balance pushed to its limits, where even the absence of water becomes a force powerful enough to shape, preserve, and redefine the Al-Ard itself. Water that should not exist. Water is often associated with life, clarity, and stability. It is expected to be transparent, neutral, and predictable. Yet in certain regions of the Earth, water behaves in ways that contradict these assumptions, shifting in color, chemistry, and biological function until it becomes something almost unrecognizable. In Western Australia, Lake Hillier presents one of the most visually striking examples. Its surface is a consistent, vivid pink, unchanged by weather conditions or time of day. Unlike optical illusions caused by reflection, this color is intrinsic to the water itself. Our scientific analysis has identified the presence of halophilic microorganisms, particularly algae such as Dunaliella salina, which produce carotenoid pigments. These compounds help protect the organisms from intense sunlight and high salinity, but they also transform the lake into a uniform pink body of water. Despite its unusual appearance, the lake is not toxic. Its chemistry supports microbial life adapted to extreme salt concentrations, demonstrating how biological systems can redefine what is considered normal. Lake Natron presents a more extreme case. Fed by mineral-rich hot springs and volcanic ash, its waters reach a pH level as high as 12, comparable to industrial alkaline solutions. This caustic environment can damage skin and eyes, and in some cases, it preserves animals in a calcified state, uncoating them in mineral deposits. Yet even here, life persists. The lake serves as a critical breeding ground for lesser flamingos. These birds rely on the lake's harsh conditions for protection, as few predators can survive in such an environment. Algae thriving in the Ilmiah provide a consistent food source, creating a system where extreme alchemia does not eliminate life, but selectively supports it. Further out in the Caribbean Sea, the Great Blue Hole offers a different kind of anomaly. From above, it appears as a near-perfect circle of dark blue, sharply contrasting with the surrounding shallow reefs. This formation is a marine sinkhole, once a limestone cave system that collapsed when sea levels rose after the last ice age. As divers descend, they pass through layers of water with decreasing oxygen levels. Below a certain depth, and the environment becomes nearly devoid of oxygen, creating a zone where most marine life cannot survive. Instead, the depths preserve geological structures, stalactites, and mineral formations that formed when the cave was still above sea level. The water here does not support life in the conventional sense. It archives it. Across these locations, water ceases to be a simple medium. It becomes a chemical system, capable of altering color, restricting life, or preserving history. Its behavior is dictated not by expectation, but by the anasa dissolved within it, the al-hararat surrounding it, and the geological context in which it exists. In these environments, water does not follow familiar rules. It defines new ones. imagination. At human scale, landscapes appear fixed. Mountains rise, valleys settle. A rock suggests permanence. But over geological time, solidity becomes fluid. Stone bends, fractures, erodes, and reforms under forces that act slowly, but with relentless precision. What emerges from this process is not randomness, but structure, patterns so refined that they appear intentional. In the American Southwest, a formation known as the wave illustrates this transformation with unusual clarity. Carved into Navajo sandstone over millions of years, its surface undulates in smooth, continuous curves. These shapes are the remnants of ancient sand dunes, compressed, lithified, and later exposed through erosion. Iron oxide within the rock produces bands of red, orange, and yellow. As sunlight moves across the surface, these layers shift in intensity, creating the impression of motion frozen in place. The formation is fragile. A single footprint, if repeated over time, can alter its surface. Access is therefore strictly limited, not for exclusivity, but for preservation. In China's Jiangye region, color becomes structure. Here, sedimentary layers deposited over tens of millions of years have been uplifted by tectonic forces and exposed through erosion. Each layer contains different mineral compositions, iron, copper, and other elements that oxidize and weather at varying rates. The result is a landscape of ridges and hills marked by distinct bands of color. These are not surface stains. They are internal records made visible through geological exposure. Wind and rain continue to shape these formations, sharpening edges and revealing new patterns over time. In central Turkey, Cappadocia presents a different interaction between geology and environment. The region's fairy chimneys are formed from volcanic ash that solidified into a soft rock known as tuff. Over time, erosion removed surrounding material, leaving behind tall, narrow pillars capped with harder stone. What distinguishes Cappadocia is not only its formation, but its integration with human history. For centuries, inhabitants carved dwellings, storage spaces, and entire underground cities into the rock. The landscape became both shelter and structure, an adaptation to environment that reflects an understanding of its properties. In Arizona's Antelope Canyon, water becomes the primary sculptor. Flash floods, though infrequent, carry enough force to carve narrow passages through sandstone. Over time, these flows create smooth, curved walls that channel light into the canyon's interior, and sunlight entering from above is reflected and diffused, producing gradients of color that shift throughout the day. These formations are not static. They continue to evolve with each storm, each shift in wind, each variation in temperature. What appears as art is the result of process. Wind transports particles that erode surfaces grain by grain. Water dissolves, cuts, and reshapes. Minerals oxidize, staining rock from within. Tectonic forces lift entire regions, exposing layers that were once buried deep underground. There is no single moment of creation. only accumulation. Across these landscapes, time is the primary architect, working at scales beyond immediate perception, yet leaving behind structures of remarkable clarity. They do not imitate design. They reveal it. Darkness is often understood as the absence of light, but in certain environments, darkness becomes a medium, one that reveals forms of illumination not dependent on the sun, but generated through chemical and biological processes occurring in isolation. In New Zealand's Waitomo caves, light emerges not from external sources, but from life itself. Thousands of glowworms belonging to the species Arachnocampa luminosa attach themselves to the ceilings of limestone caves. Each organism produces a blue-green light through a biochemical reaction involving luciferin, oxygen, and enzymes. This light is not decorative, it is functional. The glow attracts small flying insects into strands of silk that hang beneath each lava. Drawn by the illusion of open sky, the insects become trapped, providing sustenance in an environment where food is otherwise scarce. From below, the effect is disorienting. The cave ceiling resembles a night sky, filled with points of steady, cold light. But unlike stars, these sources are alive, responding to environmental conditions, adjusting brightness based on hunger and competition. This is not light as we know it. It is strategy. In Indonesia, at the Aegean crater, light emerges from a different process, one driven by chemistry rather than biology. Beneath the surface, sulfur-rich gases escape through fissures in volcanic rock. As these gases reach the open air, they encounter oxygen and ignite at temperatures exceeding 360 degrees Celsius. The resulting flames burn with an intense blue color, visible only in darkness. This phenomenon is often misinterpreted as blue lava. In reality, the lava beneath remains its usual incandescent red. The blue glow belongs to the combustion of sulfuric gases, a process that can produce flames rising several meters into the air before condensing into liquid sulfur that continues to burn as it flows downhill. The environment surrounding this reaction is extreme. The crater contains one of the most acidic lakes on Earth, and the air is saturated with sulfur dioxide. Human activity here is limited not by access, but by exposure. Even brief periods without protective equipment can cause respiratory damage. Yet within these constraints, Both biological and chemical systems produce light, independent of solar influence. These phenomena reveal an important principle. Light is not exclusive to stars or artificial sources. It can emerge from life adapting to darkness, or from elements reacting under precise conditions. In both cases, illumination becomes a byproduct of survival or transformation. In environments where sunlight cannot reach or cannot sustain, alternative systems take its place, not as replacements, but as adaptations. And in that darkness, a different kind of visibility begins to form, one that does not depend on day, but on the processes unfolding within the Earth itself. Life at the edge of survival. Life on Earth is often defined by comfort, moderate temperatures, stable water sources, predictable cycles of light and dark. These conditions form the baseline for most ecosystems and for human survival. But beyond these familiar boundaries, life does not disappear. It adapts. In environments where heat, salinity, acidity, nor isolation exceed conventional limits, organisms evolve strategies that challenge the definition of what life requires. On the island of Socotra, located in the Arabian Sea, isolation has produced one of the most distinctive ecosystems on the planet. Separated from mainland continents for millions of years, Socotra developed its own evolutionary path. Nearly 1/3 of its plant species are found nowhere else on Earth. Among them is the dragon's blood tree. Its umbrella-shaped canopy is not aesthetic, but functional. The structure reduces water loss by shading the ground beneath it and channeling moisture toward its roots. The tree's red sap, once used as dye and medicine, is a secondary adaptation, part of its defense and healing system. The landscape appears unfamiliar, not because it is artificial, but because it evolved in isolation and without external competition or interference. Every form here reflects a solution to limited water, intense sunlight, and nutrient-poor soil. In Madagascar, the Tsingy de Bemaraha presents a different kind of challenge. This stone forest is composed of sharp limestone formations, shaped by acidic rainfall dissolving softer rock over time. The result is a dense field of vertical spikes, some reaching heights of over 70 meters, separated by narrow crevices and hidden caves. Movement through this terrain is difficult, even dangerous. Yet within this structure, life persists. Species of lemurs, reptiles, and birds have adapted to navigate the Sahur, using the vertical environment as both habitat and protection. Isolation within the formations has led to high levels of endemism. Organisms evolving independently within confined ecological niches. At a microscopic level, extremophiles represent the most direct challenge to traditional biological limits. These microorganisms thrive in environments previously considered uninhabitable. Boiling hydrothermal vents, highly acidic lakes, and salt-saturated waters. Some derive energy not from sunlight, but from chemical reactions, oxidizing sulfur, iron, or methane to sustain metabolic processes. This form of life, known as chemotrophy, expands the definition of ecosystems beyond solar dependence. It suggests that life can persist in complete darkness, provided that chemical energy is available. These findings extend beyond Earth. The study of extremophiles informs astrobiology, the search for life beyond our planet. If organisms can survive in Earth's most hostile environments, similar processes may exist in subsurface oceans, on icy moons, or beneath the surface of Mars. What these ecosystems demonstrate is not resilience alone, but specificity. Life does not adapt randomly. It evolves precise mechanisms tailored to exact conditions, whether through structural design, chemical tolerance, or metabolic flexibility. At the edge of survival, life becomes less visible, but more specialized. And in these extreme environments, it reveals something fundamental, that the boundaries of life are not fixed. They are tested and redefined by the conditions in which life persists. For most of human history, these environments were not destinations. They were boundaries, places avoided, feared, or explained through myth. Regions where maps ended and uncertainty began. Early encounters with extreme landscapes rarely produced understanding. They produced interpretation. Volcanic fires became gateways to underworlds. Toxic lakes were seen as cursed. Unusual rock formations were attributed to supernatural forces. These interpretations were not irrational. They were responses to environments that defied existing knowledge. As scientific exploration expanded, these places transitioned from myth to measurement. In the 20th century, advances in geology, chemistry, and atmospheric science allowed researchers to enter environments previously considered inaccessible. Protective equipment, remote sensing technology, and controlled expedition methods made it possible to study extreme conditions directly. In Antarctica, research stations now operate year-round, collecting data on ice cores, atmospheric composition, and climate systems. Scientists drill deep into the ice, extracting samples that contain trapped air bubbles. Microscopic records of Earth's atmosphere dating back hundreds of thousands of years. These samples have reshaped understanding of climate change, revealing patterns of carbon dioxide fluctuation and temperature variation long before industrial influence. In the depths of the Great Blue Hole and similar underwater systems, divers equipped with advanced breathing apparatus descend into oxygen-depleted zones. Their goal is not exploration alone, but documentation, mapping geological structures and collecting samples that reveal how sea levels and ecosystems have changed over time. These environments require precision. A minor error, miscalculated oxygen levels, equipment failure, or environmental misjudgment can be fatal. As a result, exploration becomes controlled, methodical, and often limited in duration. In geothermal regions like the Danakil Depression, researchers study extremophile microorganisms to understand biochemical resilience. These organisms are analyzed for their ability to survive high hararat, acidity, and salinity, conditions that mirror environments beyond Earth. Such research has practical implications. Enzymes derived from extremophiles are used in industrial processes, biotechnology, and even medical research. What was once considered inhospitable is now a source of insight. But scientific engagement is only one dimension of the human encounter. There is also a psychological response. Individuals entering these landscapes often report a shift in perception, a sense of disorientation, scale, or detachment. The absence of familiar reference points, vegetation, sound, or color, creates an environment where human presence feels temporary, even intrusive. In some cases, cultural interpretations persist alongside scientific understanding. Local communities continue to associate certain locations with spiritual or historical significance, integrating empirical knowledge with inherited belief systems. This coexistence reflects a broader reality. Understanding does not eliminate meaning, it expands it. As humans move deeper into these environments, yes, the objective is no longer conquest, but comprehension. Each expedition, each measurement, each recorded observation contributes to a more accurate model of how Earth functions, but it also reinforces a consistent conclusion. These places are not designed for us. We enter them carefully, temporarily, and with the awareness that adaptation, at least in its current form, is limited. The human encounter with extreme environments is not defined by dominance. It is defined by observation and by the recognition that the planet operates according to systems far more complex than those required for our survival alone. A planet more alien than we imagined. Across continents, climates, and geological boundaries, a pattern begins to emerge. What initially appears as a collection of isolated anomalies, acidic lakes, glowing caves, shifting deserts, or frozen continents, reveals itself as part of a larger system. These environments are not exceptions to Earth's behavior. They are expressions of it. Each landscape examined is shaped by a combination of forces: tectonic movement, chemical interaction, atmospheric conditions, and time. These forces do not operate independently. They intersect, amplify, and influence one another, creating outcomes that can appear unfamiliar, even alien. In geothermal regions, heat from the planet's interior drives chemical reactions that reshape the surface. In polar environments, temperature and pressure transform water into a medium that stores history and alters light. In deserts, the absence of moisture becomes a tool of preservation, freezing entire ecosystems in place. In extreme lakes, chemistry dictates not only appearance, but the boundaries of life itself. What connects these places is not their rarity, but their consistency with underlying processes. They demonstrate that Earth is not defined by uniformity, but by variation, controlled by systems that operate across scales ranging from microscopic reactions to continental shifts. This understanding extends beyond geography. The study of extreme environments on Earth has become central to planetary science. Conditions observed in places like the Danakil Depression or Antarctic subglacial lakes are used as analogues for environments on Mars, Europa, and other celestial bodies. By examining how life adapts here, scientists refine the criteria used to search for life elsewhere. In this context, Earth becomes a reference point, not because it is typical, but because it contains within it a wide spectrum of conditions, some stable, others extreme. It offers a model of how a single planet can support both familiar ecosystems and environments that challenge the limits of biological and physical understanding. This duality reshapes perception. The idea that alien worlds must exist far from Earth becomes less certain when similar conditions are already present here. The unfamiliar is not always distant. It can exist within the same planetary system, governed by the same physical laws, yet producing vastly different outcomes. What changes is not the planet, it is the way it is observed. Examined closely, Earth does not simplify into a single identity. It expands, revealing layers of complexity that were previously overlooked. Landscapes once dismissed as anomalies become critical to understanding planetary behavior. And within that understanding lies a shift in perspective. The question is no longer why these places seem alien. It is why they were ever considered unusual at all.